Hello students. Welcome to the YouTube channel, Physics Simplified. In this video, we will discuss the second or concluding part of the river boat problems. So, without any further delay, let's jump into the discussion. In this video, we will try to find the condition for which the drift of a boatman while crossing a flowing river is minimum when the absolute velocity of the river is greater than the velocity of the boatman relative to the river. In our last video, we found that when absolute velocity of the river is greater than the velocity of the boatman relative to the river, there is drift of the boatman downstream. If the boatman steers his boat at an angle theta to PQ upstream, the drift of the boatman is given by x is equal to, within first bracket, v suffix r minus v suffix br sin theta times w divided by v suffix br cos theta. W is the width of the river. In case you have missed my last video on river boat problems, I will leave the link of that video in the description. Now, for given values of w, v suffix r, and v suffix br, the magnitude of the drift depends on the angle theta only. So, from the conception of maxima minima, for drift to be a minimum, the first order derivative of x, with respect to theta, must be equal to 0. So, d by d theta, of the expression of drift, is equal to 0. We know that 1 by cos theta is equal to sec theta, and sin theta by cos theta is equal to tan theta. So, rearranging the equation we get d by d theta of w times, within first bracket, v suffix r, divided by v suffix br, into sec theta, minus tan theta, is equal to 0. We know that d by d theta of sec theta is equal to sec theta tan theta, and d by d theta of tan theta is equal to sec squared theta. Therefore we get w times, within second bracket, v suffix r, divided by v suffix br, times sec theta tan theta, minus sec squared theta, is equal to 0. Taking sec theta common, we get w sec theta, times, within first bracket, v suffix r divided by v suffix br, times tan theta, minus sec theta, is equal to 0. Since w sec theta cannot be equal to 0, hence, the equation will be valid if v suffix r divided by v suffix br, times tan theta, minus sec theta, is equal to 0. Simplifying the equation, we obtain sin theta is equal to v suffix br divided by v suffix r. Therefore, theta is equal to sin inverse of v suffix br divided by v suffix r. So, when the absolute velocity of the river is greater than the velocity of the boatman relative to the river, the drift of the boatman while crossing the river will be minimum if he steers his boat at an angle theta, given by sin inverse of v suffix br divided by v suffix r to the line PQ upstream. Let us now calculate the minimum path length covered by the boatman under the condition of minimum drift while crossing the river. To do this, let us first calculate the magnitude of the minimum drift. If we substitute the value of sin theta in the expression of the drift, we will get the expression of the minimum drift of the boatman. So, substituting the value of sin theta and simplifying, we obtain x suffix min is equal to w times under square root v suffix r squared minus v suffix br squared whole divided by v suffix br. According to the figure, qs represents this minimum drift. Now, to calculate the minimum path length covered by the boatman, we need to calculate the distance ps. According to the figure, ps is the hypotenuse of the right-angled triangle PQS. So, applying Pythagoras theorem, we get the minimum covered path length as s suffix min is equal to under square root w squared plus x suffix min squared. Substituting the expression of x suffix min, and simplifying, the final expression of the minimum path length covered by the boatman in this case becomes s suffix min is equal to w times v suffix r divided by v suffix br. Let us now consider the case where a boatman is crossing a flowing river in a fixed or a particular direction. Many times, we face situations where the boatman is not interested to minimize the time or drift while crossing a river. Rather, he intends to reach a particular place on the other bank of the river. Like our previous river boat cases, we consider the river is flowing due east. The boatman starts steering his boat from point P with velocity vector v suffix br at an angle theta to the line PQ upstream. Suppose the boatman wants to reach point S on the other bank of the river. In this type of a situation, we generally face the following two cases. In the first case, we need to find the direction along which the boatman needs to steer his boat in order to reach point S starting from point P. In the second case, we need to find the magnitude of the absolute velocity of the boatman during his journey. Let us try to find the answer to the first case. We have already learned that the absolute velocity of a boatman can be obtained from the vector sum of the velocity of the boatman relative to the river and absolute velocity of the river. So, we can write vector v suffix b is equal to vector v suffix br plus vector v suffix r. We mark this equation as number 1. According to the figure, in order to reach point S, the boatman must be drifted along PS. This is only possible if the absolute velocity of the boatman is along PS. Now, to make calculations simple, we consider the positive x-axis along vector v suffix b and positive y-axis perpendicular to it, as shown in the figure. We also consider vector v suffix br makes an angle beta with vector v suffix r, and vector v suffix b makes an angle alpha with vector v suffix r. Let us now find the x and y components of all the terms of equation number 1. Since vector v suffix b is along x-axis, hence v suffix bx is equal to v suffix b and v suffix by is equal to 0. According to the figure, the angle made by vector v suffix br with x-axis is beta minus alpha. Hence, the x and y components of vector v suffix br are given by v suffix br cos beta minus alpha and v suffix br sin beta minus alpha. Similarly, the x and y components of vector v suffix r are given by v suffix r cos alpha and v suffix r sin alpha. Let us now write the vector forms of all the terms of equation 1. Vector v suffix b is equal to v suffix b I hat. Vector v suffix br is equal to v suffix br cos beta minus alpha I hat plus v suffix br sin beta minus alpha j hat. And vector v suffix r is equal to v suffix r cos alpha I hat plus v suffix r sin alpha minus j hat. The negative sign indicates that the y component of vector v suffix r is along negative y-axis. Substituting the vector expressions in equation 1 and equating the components of I hat and j hat from both sides of the equation, we obtain v suffix b is equal to v suffix br cos beta minus alpha plus v suffix r cos alpha. And 0 is equal to v suffix br sin beta minus alpha minus v suffix r sin alpha. Let us mark these two equations as number 2 and 3 respectively. Now, solving equation 3 by using the given information, we will obtain the value of beta. Since we are interested in finding the direction of vector v suffix b, we need to find the value of theta. From the geometry we find, the angle beta is equal to 90 degrees plus theta. Therefore, theta is equal to 90 degrees minus beta. Substituting the value of beta, we will find the value of the angle theta. This will be the answer to the first case. It must be noted that, if theta comes out to be positive, the direction in which the boatman should steer his boat will be west of north. But, if theta is negative, the direction will be east of north. Now, if we substitute the value of beta in equation 2, along with all the given information, we will get the magnitude of the absolute velocity of the boatman. This will be our answer to the second case of this section.